Okay, so far we have seen arithmetic and logical instructions, addition and subtraction with the different modes like adding carry, adding immediate word or something like that, multiplication and division operations, and logical instructions like AND or XOR, shift left, shift right, rotate left, rotate right, arithmetic, shift right and data serialization. We also seen in the last the BCD and how packed BCD are can be converted between ASCII and other way around. Now we are getting this discussion into more details or deeply with the branches and loops, which I already mentioned that they are quite important because when we are performing operations, we might need to jump to somewhere else to satisfy some other conditions. And some of these are coming with some conditions, and other ones are just coming without conditions. Or we might need to repeat some sequence of instructions, which we call them loops. So we might need to create loops. So rather than writing the same instruction as many times as we can, which might cause a lots of repetition and just you are just wasting a cycle, instruction cycles. Rather than doing that, we can actually create loops and we can go through that instructions and jump and restart again and so on using counters and so on. Right. So if we want to create a loop or what we call is a looping in AVR, we can actually do that using conditional statements, which we call them branches. And so, for example, you can do an addition, repeated addition of two numbers, maybe 5 times, 10 times, or 15 times. Now, you are actually wasting the code space if you are just repeating the same instruction, like add R20, R21. Add R20, R21, and you're repeating that maybe 10 times. Now, as we are wasting a code space, and if you want to have like 50 or maybe 100 repetitions, this could be a problem. So rather than doing that, maybe we can use, as we already mentioned, branch not equal instruction. So we can check if the counter is 0 or not. So at this point, we are decrementing a register value. And if it's not 0, then go back and start again, jump to a label and start again. So I can show you an example of this. Let's say we have got LDI R16 0 and LDI R17 3. And what I want to do is add R16, R17. And I repeat that. And I repeat that. And it goes, let's say, 50 of those and R16, R17. Okay, so this is possible. But as I said, you are just wasting your code space by repeating the same instructions. So rather than doing that, maybe I can write it next to it. I can create a counter. And I'm just writing the structure of the coding. Create a label, L1. And I say over here, add R16, R17. Okay. Then somewhere here, I define that counter. Let's say LDI R20 equals 50. Okay. So then I define R16, R17 like we have done it over here. These will be included over here. Then what I do is I say decrement instruction, register -1, decrement R20, let's say, and I use branch instruction, branch not equal, and I'll say if the branch is not equal to 0, not equal means Z flag to be 0, then it will go back to L1 and add again. So rather than having these long code, I can just do that, including the definitions, one line, two, three, four, five, six. With the 6 lines, I can do the same operation. So in the last two instructions, the R20 is decremented, and if it is not 0, it branches, it jumps back to the target address, which is referred over here as L1, and it repeats that again until the counter is 0. So before we start it, as you can see over here, we load the counter. So we know how many times we are going to repeat that. And we know that BRNE refers to the Z flag, but you can use different branches. You are not restricted with BRN. So we have seen these branches, and we can do this. So I'm going to solve a simple example just to make sure that we understand what's going on. Write a program to clear R20, then add 3 to R20 10 times, and send the sum to port B. Use 0 flag and BRNE instruction. Okay, now we need to clear R20 first, and we need to add 3 to R20 10 times. So clear, add 3 10 times, and send to port B. And we have to use BRNE instructions. So these are all highlighted in the question. Okay then. So let's first define our counter. LDI R16. We know we are going to repeat it 10 times. So we write 10. And then we have to clear R20. LDI R20, it's going to be 0. So all registers are going to be 0. Clear means setting everything to 0. Then I have to define 3 that I want to add to R20. So R21 is 3. And then I do add operation at R20, R21. So I'm adding 3 to R20 and so on. Now, like I have shown over here, I have to add a label because I'm going to repeat that. So I put that in red. Then I have to decrement my counter after each addition. Decrement R, our counter is R16. And then check. So after the condition, the decrement, we have to check it because the status register is updated. BRNE, I'm just going to put the same color, L1. And then the last state says send the sum to port B. So when it is completed, it's not going to repeat it. And when it is jumping out of the loop, it will be going to send the value to port B, and that will be the value of PART3. Okay, so if you write the comments as well, then R16 equals 10, R20 equals 0 over here, and R21 equals 3. Okay, and here R20 equals 0 plus 3. Okay, and then this will carry on. And decrementing, this is going to be 10 minus 1 because we are decrementing. Repeat that. Repeat until 0. And then after 10 addition, then we'll have port B equals R20 value. So that's how we can use actually the branches for looping. We can create a counter, then we define the condition and we branch. So the question comes now, what will be the maximum number of times the loop can be repeated? In this example, for example, as we are using R16, R16 is an 8-bit register. So 8-bit register can hold 2 to the power 8, 255 locations. Okay, so that means the loop can be repeated 255 times, not more than that, as this is an 8-bit register. What you can do is, if you want more than that, you can create a loop inside of a loop. So you can have a one counter that goes up to 255, then you can have another counter that goes up to another, let's say 100. So when one of them is ending, the other one is going on, and then it will increase or decrease it. And you can create a nested loops or loops inside of a loop. Okay, so if we carry on from the slides, now jump and calls are important in execution of the instructions. So normally what we do is, this is a typical C code. Now A is equals B plus C, we perform that operation, and then you do C minus 2, and then we do D is equals A plus C. So CPU first execute the instruction line 3, then adds B and C. So over here, then executes line 4 and line 5. So this is going in a sequence. Now, sometimes when you're doing some operations, you might need to jump to another instruction rather than the next instruction. This can be a conditional instruction, like an if statement, like a loop that we already mentioned, or it can be another function. So when you are doing A plus B or B plus C, then jump to somewhere else and do something else. For example, if you don't want to execute the next instruction because of a condition, so you initialize values, you check A. If it is equals 8, then C is equals 6, otherwise C is equals 7. So that means until you satisfy that, you don't get into that C is equals 6. You always go there because of not satisfying it. So as A is 2 over here, this instruction will not be executed and this will be executed. Another one, so this is creating for a loop. Now you initialize some variables again. You say A is 2, and if A is when A is less than 4, you just repeat and you add 1 to A. Now we execute line 4, line 5, okay, and then we go again back to line 4 and line 5, line 4, line 5, until we reach a certain point that A is equals, A is less than, A is greater than 4, A is greater than 4. So when A is greater than 4, you jump out and then you execute line 6. Another one is not executing the next instruction because of the calling function. So you initialize variables rather than executing line 6. As you are calling a function, without getting in there, you just jumped to line 8. Okay? So we execute that one. When we finish that one, we return back and we execute it. Okay, so we execute the function and return back over here and execute c is equals a plus 3. And this is how we can use call and jump instructions, which we are going to see those in details with the assembly language as well. Now, in assembly language, there are two groups actually for the instructions. So either they are jump, which are used in the loops within the conditional code segments. So they can be unconditional or conditional jumps. Or you can use a call, which you can use it for calling a function. So you can make a function's calls. So jump instruction is one of the most used instruction, which changes the program counter and causes the CPU to execute an instruction other than the next instruction. Because what we have seen is program counter is always pointing to the next instruction. When you are using a jump instruction, it will not go into the next instruction. It will just jump to another place based on the given in the opcode and the operand. So there are two kinds of jumps, unconditional jumps and conditional jumps. Now, unconditional jumps, when CPU executes an unconditional, it jumps unconditionally without checking any condition. Okay, so R jump, relative jump, or the jump instructions are conditional. It doesn't check. It's looked like an if statement. It just says, okay, jump to somewhere else and execute that. But conditional jumps, like branches, like branch not equal, branch equal, and so on, it checks for a condition. So if the status flags or in the status registers are set or not set, and then do the jumps. Okay? Otherwise, it will execute the next instruction. Now, we are going to see these jumps in details. So unconditional jumps, these are three types, relative jump, jump, and indirect jump, which is I jump. Now, we actually label the location where we want to jump, okay? So add R16, R17, without any condition, repeat it, okay? So we label the location where we want to jump. It's just a unique name. It's not going to be a long name, just a short one. And then for the R jump, you just write the same label. So this causes the label, the CPU to loop in that until you get some point. Now, you can have this like a jump instruction with, you just state the operand with the direct jump, okay? So the program counter there, it jumps to, let's say, line 10 or line 16. And relative jump, which over here is shown, you are actually using the operand and the program counter. Okay, so they have got a different properties over here with jump and relative jump. Now, jump is actually a long jump, we call it, the direct one. So it's a unconditional that can go to any memory location. So we can have a, I'll show you from here. We can have a 4 million words address space of the AVR, and we can jump to any part of it. It is a 4 byte of instruction, as you can see over here. Okay, and 10 bits are used for the opcodes. So 4, 7, 10 bits, which are in the yellow part, they are used for the opcode. This is specific for the jump instruction. It's not going to change. But the operand is actually telling you, which is 22 bits, it's going to give you a span bit in 4 million words or 8 megabytes of program memory space. So it just tells you which part of the program memory you want to jump with this operand. So as you can see highlighted over here, the red ones are the opcodes and the gray ones are where we are going to jump, which is going to be line 6 in this example. So this is one of the largest instruction. It executes in 3 cycles and it's 32-bit instruction. So 22-bit address is actually jumping from 00000 to 3FFFF. So this is the memory location for 4 million words. Okay, so this is jump instruction. Let's see how it is operated. Now, program counter, we have got it, and this is the jump instruction, which is calling the destination as line 6, okay, which is over here, jump label name, line 6. This is all encoded in the machine code as 40C, and the operand is 006. So LDI R1615, LDI R17.5. As you can see, the program counter starts to increment when we start to fetch the first instruction. Then in executing the second instruction, then we are fetching the first instruction is executed, second one is fetched, and the program counter points to the next one. And then it goes like that. So when we are in address 2 where we have got jump label, this is actually, as we have got jump over there, this operand is moved to the program counter because the jump instruction telling the program counter to change it to line 6 because this is where I want to jump. So we jump over there. We are in line 6. Program counter points to 7. It executes it, and then it executes the next one. Jump label, so it's going to return back again. So this is going to be 6 again, and it will return back to 6. Okay, and this is how the jump instruction is operated.